Hoffman. And then when it comes to question session, you can either put your hand up or put your questions in chat. And remember that this is being recorded and our monthly seminars are appearing on the HITRIplus YouTube. So you always have a chance to refresh and look back, and also share the link with your colleagues who can't possibly join us today. So 5:05. So Aswin, so let me welcome Aswin Hoffman. It's a great pleasure. And he's really talking about a topic which is really hot at the moment. And he's going to tell us about integration of MRI and proton therapy. And the most important thing is motivation challenges and roadmaps, because we know it takes a long time from the idea, motivation, getting the funding and actually getting there. So it's always interesting to hear the story as well as the outcome. And so Professor Hoffman obtained his master's degree in electrical engineering and started becoming interested in radiation oncology in 2002 when he joined the radiation oncology of Radboud University Medical Center. And since then he's been progressing, and I've been watching him go through also the, first the MRI-guided radiotherapy with photons, and now MRI-guided proton therapy. So that will also be interesting to hear about this gradual road. And as I said, for imaging, it's always been interesting, because ever since I met Wolfgang Enghardt 20 odd years ago, Oncore in Dresden have always been one of the centers for imaging. So it doesn't surprise me that we are going to hear about this latest exciting innovation from somebody from Dresden. So Aswin, please, the floor is yours.
So thank you very much, Manjit. Thank you also, Peter Grübling, for inviting me both to give this lecture during this seminar. It's a real pleasure to give you an update on the exciting project that I have been running here at Oncore in Dresden since 2015. Let's start with a little bit of background information on proton therapy. I think it is safe to say that the clinical benefit of proton therapy for moving tumors is still poor.
Please turn your microphones off, please. Sorry, Aswin.
No worries. And we know, of course, from comparative treatment planning studies that proton therapy should be more effective than photon therapy, because the integral dose is much lower in proton therapy or in particle therapy than in photon therapy. And this is, of course, due to the fact that we have the steep dose gradients at the distal end of the Bragg peak. However, from a clinical point of view, there is still limited randomized evidence showing the real clinical benefit of proton therapy relative to, for example, IMRT with photons. There are some treatment sites, some body sites where a toxicity reduction has already been shown. So there is level 1 evidence that proton therapy has a clinical benefit over IMRT for pediatrics, brain and esophageal cancer. But for example, for non-small cell lung cancer and for liver cancer, such a clinical benefit has not really been shown yet. And if we more carefully look into these type of organs, esophagus, lung and liver, what they have in common is that they move during dose application. So the hypothesis here is that the targeting accuracy of particle therapy and proton therapy in particular is compromised by the lack of 4D image guidance during dose application. So we all know that proton therapy dosimetry is highly susceptible to anatomical changes and setup inaccuracies because it has a greater sensitivity to density changes along the beam path due to organ motion and tissue deformation. And some volumetric image guidance in proton therapy is already available in most of the clinics, but it is lagging behind image-guided radiation therapy with photons. So I think that Two-dimensional orthogonal radiography is widely available through all clinical proton therapy centers now. Some of them, for example, we here in Dresden have an in-room CT available. Onboard three-dimensional cone-beam CT is coming commercially available and has already been installed in some centers on new equipment. But if we look to a survey that we did as European Particle Therapy Network back in 2018, what we learned from that study is that approximately half of the proton therapy centers have the capability to image the patient in treatment position. And also from a study performed by the PT Koch, we know that approximately 70% of the operational proton therapy centers that have been established after 2015 have some kind of volumetric image guidance available. But nevertheless, for moving tumors, there is still a lack of fast imaging and high soft tissue contrast imaging during dose delivery. So that means that currently the full dosimetric benefit of proton therapy is not yet completely exploited. And we have to face two problems. So the first one is that prior to treatment, but also during treatment, we do not know always exactly what we are shooting at because we cannot see where the tumor is because of the limited imaging capabilities. And the second problem is that we are not able to see what we hit because we cannot visualize the proton beam in real time during dose application. So therefore, actually, currently, we cannot accurately localize the moving tumor during dose delivery, and we have no means to assess the beam range and control the beam in real time because of the lack of real-time imaging. And therefore, currently for moving tumors, we cannot achieve a greater targeting precision with proton therapy, simply because of the fact that imaging tools are currently lacking to overcome these critical limitations. So as I've shown here on the right-hand side in that picture, to some extent, we are blindfolded and we do not always know exactly what we are shooting at. And certainly we do not always know what we are hitting. And this does not only play a role, of course, in particle therapy, but also in image-guided phototherapy. And these arguments were the motivation to start developing the MR-LINAC for the photon therapy world many years ago, 20 years ago, approximately. So the idea here was to bring together the exquisite soft tissue contrast that magnetic resonance imaging can provide, and now to combine that with the superior dose conformality that proton therapy offers. And we know, for example, that the motivation to develop the MR-LINAC was that approximately 65% of all cancers recur in organs like the lung, the prostate, the breast, the cervix. And 6 out of these tumors, of these cancers, are very difficult to visualize with CT imaging because CT imaging has a low soft tissue contrast. So even this is a paper that was published in 2017 in Medical Physics with the title Future of Medical Physics, Real-Time MRI-Guided Proton Therapy. And if you look at the authors of this paper, these are the people that developed the MR-LINAC, from the Australian MR-LINAC program. And even Professor Jan Lagendijk from the University Hospital in Utrecht in the Netherlands, he tweeted this message back in 2014 when there was a discussion in the Netherlands on the installation of 3 particle therapy centers. And he said here, as you can see, protons must become MRI guided or will not be at all. So let's see if we would go for this approach, the full technical integration of magnetic resonance imaging and proton therapy. So what are the advantages of having an onboard MRI machine? Well, of course, first and for all, MRI provides an excellent soft tissue contrast. And this, as you can see on the right-hand side of an MRI of a patient, an MR image of a patient showing the abdomen, we can have an improved organ depiction, which would allow us to make a more accurate tumor volume delineation in comparison to CT, where the soft tissue contrast is lacking. Furthermore, we don't have any ionizing imaging dose during MRI scanning, which would allow us to do continuous imaging. Furthermore, MRI provides also real-time imaging capabilities, which allows us to capture organ motion. And last but not least, of course, we can also do functional MR imaging for treatment response assessment. So the whole idea here is schematically represented with this little movie, is to fully integrate MR and proton therapy with in-beam MR guidance. So this is what we call MR integrated proton therapy, abbreviated as MRI-PT. And this will allow a synchronization of the tumor position and dose delivery to increase the targeting precision. This is what we call the treat what you see approach. But you can also turn it around. If you would have such a device, an in-beam MR scanner, it would maybe also give you the opportunity to see what you treat. If it would be possible to detect MR signatures that are indicative of the proton dose delivery. In other words, wouldn't it be great if MRI could visualize the proton beam during dose application in real time? And in this talk, I will guide you through these two approaches: treat what you see and see what you treat. But of course, there were a lot of knowledge gaps and research hypotheses and uncertainties when we started this project here in Dresden in 2015 from different aspects, both from engineering point of view, from a medical physics point of view, from an MR imaging point of view, but also, last but not least, from a radiobiology point of view. So let's start with the first one. So the engineering challenge was to see if we can unravel the complex electromagnetic interactions between an MRI and a proton therapy system. I will show you that in the next slide, because a proton therapy facility is an electromagnetically dirty environment. There are different magnetic fields. There is RF interference from the cyclotron, for example, and to have an excellent MR image quality, we need to find a way to block these external electromagnetic interferences. So we need to understand how this magnetic crosstalk between the MRI system and the proton therapy system works in order to be able to compensate for this crosstalk. From a medical physics point of view, because protons are positively charged particles, and when they move through a magnetic field, they will be impacted by the Lorentz force, and this will change our dose distributions. So here the question is, how can dose distributions be accurately delivered, but also measured in the presence of the MR magnetic field? We need to be able to quantify the dose distortions due to the presence of the magnetic field. This needs to be taken into account both during the treatment planning and also during the treatment delivery phase, but also just for dosimetry purposes, because the magnetic field can have an impact on the response of the dosimeter. Then regarding this beam visualization topic, which is of course very challenging and very interesting. So here the research question is, can we render MR imaging fast and sensitive enough to provide online beam range monitoring? Is it possible to visualize the beam with MRI in relation to the anatomy of the patient in real time during dose delivery? And I will show you that it is possible to some extent. And last but not least, there could also be a synergy, of course, between the magnetic field and the tissue response. So can we grasp the synergy of the tissue radio responsiveness under magnetic field exposure? Because the directionality of the magnetic field relative to the beam direction, but also the strength of the magnetic field, might have an influence on cell killing and tissue response, both for the tumor, but also for the organs at risk. So in this talk, I will focus on these 5 aspects where we have come up with a kind of roadmap to bring this in-beam MRI-guided proton therapy into a clinical application. And the first step that I will now focus on is MR scanner integration within the proton therapy facility. So when we started this project, we made a risk analysis, a risk assessment. And of course, the first risk, the highest risk, would be the interaction of external magnetic fields with the magnetic fields of the MR scanner. And this could lead to a degradation of the MR image quality. So where do these external magnetic fields come from? As I will show on the next slide, there is a cyclotron, there is a rotating gantry in the treatment room next to the room where we would like to install the MR scanner in. And then, of course, there is the beamline with the beamline transport and focusing magnets, but also the beam steering magnets for active pencil beam scanning could have an impact on the static magnetic field of the MR scanner. But there would also be, as I mentioned before, because of the Lorentz force, there would be an interaction of the beam with the MR magnetic field. So this is a little bit different than for photon therapy, because here the primary protons are also, so the primary particles are also affected by the Lorentz force during the transport through the fringe field and the imaging field of the MR scanner. And of course, also the secondary electrons, like in the MR-LINAC, will be affected by the presence of the magnetic field. And this will lead to dose distortions. I'll come to that later on, but it will also affect the dosimeter response in the presence of the magnetic field. Then, of course, there is also the interaction or the potential interaction of the proton beam with the transmit and receive antenna of the MR scanner. In this talk, I will not address this topic. What I also will not address is the radiation hardness of the magnets of the MR scanner. I will briefly touch upon the effects of the MR-only based treatment planning, because in the end, for a fully integrated and online adaptive workflow, we would like to get rid of the CT imaging to do a replanning. So this whole concept is about MR-only based treatment planning for particle therapy. And what about the beam range detection with beam visualization? So when we did the magnetic survey, this is a schematic representation of our particle therapy center here in Dresden, where you on the left hand can see the therapy room with the big gantry, where we have 110 tons of ferromagnetic material close to the experiment room where we would like to install the MR scanner. And then in the room next door, we have the cyclotron. Now we know that the cyclotron has a static magnetic fringe field that would overlap with the magnetic field of the MR scanner if we would install the MR scanner here in the experiment room. Fortunately, these effects, because it's a static magnetic field, can be corrected for during the shimming of the MR magnet. So that's not a risk. But then the beamlines, the beamline magnets. So the magnets in the quadrupole magnets and the dipole magnets in the beamline, what we found out is that these can have a significant effect on the B0 field of the MR scanner, so the static magnetic field of the MR scanner. As soon as the magnets are energized, they will generate a magnetic fringe field that is dependent on the energy of the proton beam requested. And this magnetic field will overlap definitely with the magnetic field of the MR scanner. So we need to have a kind of synchronization between image acquisition and requesting the beam. We found a way to compensate for that in such a way, I will show you that in a few slides, that we can acquire good quality MR images during proton irradiation, taking into account the external magnetic fields from the beamline magnets. And what about the gantry? I already mentioned it. So this gantry weighs 110 tons, is made of ferromagnetic material. As soon as the gantry rotates in the therapy room next door, it will change the environmental magnetic field in the whole facility. Fortunately, this effect turned out to be very small in terms of magnetic field strength, though it has a negligible effect on the static magnetic field of the MR scanner. So that is good news. So back in 2018, together with IBA, we developed and installed a first generation prototype to show proof of concept of in-beam MR imaging during static beam delivery at our horizontal beamline that you can see here. So here you see the last dipole magnet that bends the beam into the experiment room. Here you see the quadrupole magnets to focus the beam in horizontal and vertical direction. And this is our 0.22 Tesla C-shaped open MRI scanner with a homemade Faraday cage to block external radio frequency signals. And if you very carefully look here into the wall, there is a little hole with a waveguide or a beam guide, as we call it in this way, that is attached to the beam line that you can see here. So we can bring in the proton beam without any interaction of the wall of the Faraday cage. And what you can see here in the middle of the MR scanner is a knee coil with a dedicated quality assurance phantom, from which the MR images are shown here on the right-hand side. So this is a typical image of this QA phantom acquired with the beamline off. There are no beam transport, but also acquired during beam on. So we actually irradiated this phantom centrally, and during irradiation, we acquired these images after compensating for the external magnetic field produced by the quadrupole and dipole magnets. And what you can see is that there is hardly any difference in image quality. So I think from this we concluded that the MR image quality is preserved during simultaneous static proton beam delivery. Then later on in 2018, our second horizontal beamline with a dedicated pencil beam scanning nozzle became available in the experiment room, and we moved over the MR scanner because the MR scanner was installed on a mobile trolley, as you can see here. So we rolled it over to the second beamline, and now of course we are very close to the scanning magnets. And we did the same experiments, and what we found out is that when we scan the proton beam in horizontal direction, it has a dramatic effect on the image quality, as you can see here. So if we scan the beam in horizontal direction, either with 9 equidistant spots or 17 or 33 equidistant spots, you can see these so-called ghosting artifacts. Not if we scan the beam in vertical direction. The reason for this is simple. It's twofold. First of all, the scanning magnets that scan the beam in vertical direction are further away from the MR scanner than the scanning magnets that scan the beam in the horizontal direction. But that's not the most important reason. The most important reason is that in order to scan the proton beam in the horizontal direction, the magnetic field inside the scanning magnets is either parallel or anti-parallel to the static magnetic field inside the MR scanner. So this means that in this case, when we scan the beam in the horizontal direction, there is a maximum crosstalk between the fringe field of the scanning magnets and the static magnetic field of the MR scanner. And that is why we see these kind of effects. So we are not the only one that observe these effects. Also, our colleagues in Heidelberg, they also have an in-beam MR scanner at the Heidelberg Ion Beam Therapy Institute, so at HIT, where they have the Artemis project, and have the capability not only to apply scanned proton beams, but also to apply scanned helium and carbon ion beams. And what they did with their 0.25 in-beam MR scanner at the horizontal active raster scan research beamline is that they scanned a homogeneous phantom, applied those spots, so a raster scan both in vertical direction and in horizontal direction, and they plotted a profile in horizontal and vertical direction through this homogeneous phantom. And they also found that if they scan the beam in the horizontal direction, the image quality is degraded. And this is also due to the fact of the magnetic fringe fields of the scanning magnets, even though their scanning magnets are much further away. I think it's approximately six meters away from the beam isocenter. In our case, it's approximately 2.5 meters. So this tells us that we are looking at the same kind of effects, and we cannot ignore this. So what we need to get rid of these imaging artifacts is magnetic shielding. And this is why, together with IBA, we have developed a so-called finite element model of our pencil beam scanning beamline. So each individual component, as you can see here on the right-hand side, from the scanning magnets, the door of the X-ray tube here, the interfaces, scanning magnets, quadrupole magnets, everything has been modeled. All materials have been put into this computational model, which allows us to investigate or to simulate the magnetic fields that are produced by the scanning magnets when we scan the beam in horizontal or vertical direction. This is work done by Dr. Bradley Oborn from the University of Wollongong in Australia, who is a real expert in magnetic modeling. And what he did, and this is a top view of our dedicated pencil beam scanning nozzle, where you can see here the last pair of quadrupoles and the Y and X scanning magnets. He did not only use this finite element model to predict and simulate the magnetic fields produced by it, but he also coupled it to GN4. So we're also able to transport a proton beam, a proton pencil beam, through this magnetic field and see where it ends up in the plane of the beam isocenter. And here on the right-hand side, you can see some results of his computational modeling, showing for a 200 MeV regular scanning pattern, those spots that are applied. And you have to believe me, I won't show any further quantitative details, but the positions that were planned based on the current settings of the scanning magnets, as you can see, show a very good correspondence with the intended positions on this regular scanning pattern. So this tells us that the model, that we have the integrated model of the magnetic fields, components of the magnetic fields produced by the scanning magnets, and also the GN4 simulation is actually very good. We validated this, of course, also experimentally by doing magnetic field measurements around the scanning nozzle. So one of the projects that we currently have is to develop concepts for passive magnetic shielding, so to shield the magnetic fringe fields produced by the scanning magnets from the magnetic field of the MR scanner. We're looking at different materials, we're looking at different geometries, but for the sake of time, I will not go into any further detail. In the meantime, we have also generated or installed a second generation prototype system, which will be used for a first in human application. So this scanner, as you can see here, is built into a more professional RF cage made of aluminum. The scanner, which you can show here on the right-hand side, weighs about 15 tons. And because there are also other investigators here at Oncoray who would like to do their experiments without the presence of the MR scanner in front of either of the two beamlines, the scanner had to be mobile. So that is why we installed it on a mobile air cushion platform, as you can see here. This is me during Corona times playing around with the MR scanner on this air cushion platform. Here you can see in the middle picture, you can see that the in-beam MR scanner has been attached to the pencil beam scanning nozzle. And this is an in-cage view of this RF cage with a dedicated patient couch. Here you can see an arm holder that I will show in the next slide, because we are in the process to prepare a first-in-human treatment of patients with soft tissue sarcoma of the extremities. Because we know in these type of patients, we know that from studies done, longitudinal studies done in the Netherlands based on daily cone beam CT imaging, that in approximately, for photon therapy, that in approximately 60% of the patients, anatomical variations will occur during the course of treatment. And that in approximately 10% of these patients, a planned adaptation is needed. And we believe that even with proton therapy, these numbers will even be higher because, as you know, proton therapy is more sensitive to anatomical variations than photon therapy. MRI provides excellent soft tissue contrast to localize the tumor, to see if there is any tumor change, any swelling of the tumor going on. So it will give us an excellent opportunity to once a week put the patient inside the MR scanner with his or her arm stretched out laterally, take an MR image, and based on that weekly MR image, decide whether we need to adapt the treatment plan or not. But the patient, as I said before, will indeed be treated in this imaging position in the presence of the magnetic field. Then we have last year, after 5 years of preparation since 2018, we have installed a whole body scanner also inside our experimental room, because the 2 prototypes that I showed you before are not fast enough for real-time imaging. And this is, of course, the ultimate goal, to have real-time MR imaging capabilities during those applications. So back in 2021, we started the development of this rotatable MRI system together with industrial partners. And this is merely the LINAC MR system that has been developed by Professor Gina Falone at the University of Alberta in Edmonton, Canada, and which is marketed now by the company called Magnetics. So what you see here is an artist representation of our horizontal dedicated pencil beam scanning beamline together with this whole body MR system. And the magnet has 2 orientations, as you can see in this image. So here the magnets are in a horizontal position. The patient is lying on this couch here. And in this case, we have the beam, the proton beam, perpendicular to the static magnetic field, which means maximum impact of the Lorentz force. But if we rotate the MR scanner by 90 degrees, and there is a hole here in the yoke of the MR scanner where we could fire the proton beam through, this would allow us to have the proton beam parallel to the static magnetic field. And this means there is 0 impact of the Lorentz force, little impact of the Lorentz force, I have to say. There is no lateral beam deflection. There will only be a twisting of the radiation field due to the presence of the magnetic field. This is another schematic representation of that magnet, here with the magnets in vertical position, here with the magnets in horizontal position. Here you can see the treatment couch that has a rotation angle of ±10 degrees. Both the magnet and the treatment couch are installed on air caster platforms, again, that can be separated from each other. To give you an impression, this couch weighs about 1,200 kilograms. The magnet weighs about 35 tons. Then, of course, to do MR imaging, we have to block the external radio frequency signal. So that means that we had to build a Faraday cage around it, also installed on the mobile air cushion platform. It's a specific type of magnet technology. Of course, the magnet has to be open to be able to bring the proton beam in without any interaction of components of the magnetic of the MR scanner, for example. So that is a reason why we could not take normal MR-LINAC systems, because there we would have to fire the beam through the cryostat, which would have an impact on the quality of the beam. This magnet is based on high temperature superconducting magnesium diboride technology, which means that it is cooled by gaseous helium, not by liquid helium like normal MRI scanners. So this has the consequence that we do not need a quench venting pipe, which is a tremendous advantage, because there is 3 meters of concrete everywhere in our radiation vault. And you cannot simply open this to install such a quench pipe because of radiation protection arguments. Furthermore, as I showed you before, the magnet is rotatable. And another advantage, although it has been tuned for MR imaging at 0.5 Tesla, because it's an electromagnet, the field strength is scalable between 0 and 0.5 Tesla. This, of course, is also very interesting for radiobiology studies, to see if there is any impact of the directionality and the strength on the magnetic field to cell response. This rotatable magnet, as is shown here, with the magnets or the beam and static magnetic field in parallel orientation, would also allow an upright whole body treatment. That's also one of the aspects that we are very interested in. 0.5 Tesla provides an excellent contrast to noise ratio for the thoracic region. We all know that in the thorax, the lungs move during breathing. If you go to a higher magnetic field strength, the contrast to noise ratio is worse. So that was also one of the reasons why we chose for mid-field MR scanner instead of a high-field MR scanner. This scanner has also the capability to do real-time imaging at 4 frames per second, which would allow us to do tumor tracking and beam gating. And furthermore, as I mentioned before, the scanner is mobile because it has been installed on an Aircaster platform. Here you can see, last year we installed it. Here you can see some pictures of the experimental room with the 2 large RF cages, the one for the magnet, the one for the couch, some additional components, the gradient amplifier, cooling system. And you can see that we tried to keep as much space as possible in the research room. So a lot of equipment of the MR scanner, the cooling system, is installed outside of the radiation vault. So that is why there are a lot of power cables, signal cables, the gaseous helium flex lines, the cooling water are here installed on a crane system that can move with the MR scanner, because the rest of the equipment is installed in another room on top of the research vault. Here in the picture on the right-hand side, you see that both cabins have been separated. So the one with the couch, the one with the magnet. This is a more close-up. Here you see again on the left-hand side the dedicated pencil beam scanning nozzle with the gantry of the MR scanner. In this case, the magnets are vertically oriented. And this is a close-up picture also together with the patient couch. So that is where we currently are. This is a little movie to give you an impression of the size of the system, how it is closely connected to the pencil beam scanning nozzle, as you can see here. This is how we lift up the cages, how we decouple and separate the cages. This is all done with compressed air. Here you see it, it's lifted up. And then it's very simple because the couch cabin is not that heavy. 2 people can just move this cage around. And for the magnet, because it's 35 tons, we have included MR compatible drive units underneath. So here you can see that one of my colleagues is steering this 35 tons couch or cabin with millimeter accuracy, moving it close to the pencil beam scanning nozzle. Okay, let's go to the next step, which is treatment planning and dosimetry. Go a little bit faster. So the colleagues in Heidelberg, as I mentioned before, also have a 0.25 in-beam MRI scanner. And they show the effect of the presence of the magnetic field on the deflection of the beam, here shown on radiochromic film for the different particles. And what we learned from this experiment is that the lateral beam deflection is inversely proportional to the particles' momentum, here for protons, helium ions, and carbon ions. Then with our second prototype scanner, we did an experiment to see which characteristics of the beam and the radiation field are influenced by the presence of the magnetic field. So what we did is that we moved our 0.32 MRI scanner close to the pencil beam scanning nozzle. The static magnetic field of the MR scanner is perpendicular to the beam transport direction, and at different distances from the MR isocenter, we put vertical to the dosimeters. And we fired the beam and measured what happened to the beam as a function of distance and a function of beam energy. And this is what we found. So here, for example, for location A, in blue, you can see a 15 times 15 square centimeters radiation field without the presence of the magnetic field, which will, of course, due to the divergence of the beam, become wider at the different positions B and C. But now in the presence of the magnetic field, here represented in red, is the radiation field size as it is measured in the presence of the magnetic field. And you can immediately see that due to the presence of the Lorentz force, there is a shift, a lateral shift of the radiation field. That, of course, is also distance dependent, but there is not only a shift, there is also a deformation of the rectangular radiation field. So, for example, here for this location D, you can see there is a very large lateral shift of 18.6 centimeters, but also the field edges are here on the left-hand side more compressed, whereas the field on the right-hand side is stressed. So we don't have a rectangular field anymore. We have a kind of trapezoidal field. And this is because of the presence of the static magnetic field of the MR scan. Now you could, of course, simply say, okay, we can compensate for this. We just shift this field, this radiation field, back to its original position. But even then, if you would do that, as I explained before, you can see that there is no rectangular field anymore. There is a deformation in such a way that we have a trapezoidal field instead of a rectangular field, which need to be taken into account during treatment planning. Also, if we look at the individual dose spots without the magnetic field, here, are the spots on the left field edge, here the spots on the right field edge. Now, if we measure that in the presence of the magnetic field, you can see there is a spot rotation here for the individual spots. So that means that there is distortion of the spots that depends also on the location where you measure, and of course also on the beam energy and the distance from the beam isocenter. So the message here is that during treatment planning, we need to take into account this three-dimensional magnetic field distribution. So that is why we had developed for our second generation MR prototype an innovative method to fully map out in 3D the magnetic field where the proton beam could travel through. And this is a schematic representation of that, a color-coded schematic representation of that magnetic field. And we have a research collaboration with research laboratories to be able to import this three-dimensional magnetic field into their treatment planning system and do the dose calculation under the presence of the magnetic field in a Monte Carlo type of way to take the beam deflection and the spot distortion into account. A lot of publications have already touched on the topic of dose calculation and dose optimization in the presence of the magnetic field. I won't go into all details. The main difference between them is that some of the methods are based on Monte Carlo methods. The other ones have tried to develop analytical methods showing the impact of the static magnetic field of the MR scanner, but also the dosimetric impact of the dynamic gradient fields that are switched on during image acquisition. Different correction strategies have already been proposed to account for this beam deflection. And it has even been shown by different people that plan quality, the same plan quality can be achieved with magnetic field as without magnetic field. I refer to two papers here by Lucas Borrigo from Heidelberg and again Bradley Oborn from the University of Wollongong, showing that those distributions can be fully recoverable in the presence of a transverse magnetic field. Not, by the way, not only for a transverse magnetic field, both for an inline fields where the beam is parallel to the static magnetic field and also for cross-line fields where the beam is perpendicular to the static magnetic field. Then what about detector response in the presence of the magnetic field? This is work mainly done by the group of Dr. Hermann Fuchs at the University of Vienna. And he showed for different type of ionization chambers for absolute dosimetry that there is a small but significant effect depending on the strength of the magnetic field, depending on the type of ionization chamber used. It's not rocket science. We all know how this works. We have to apply correction factors to the readings in order to compensate for these effects. Then what about the electron return effect in protons in a magnetic field? We know that this effect can be very large for photon beams in the presence of the magnetic field, even up to a local dose increase of approximately 30% over the first few 10, let's say first 10 millimeters at a tissue air interface. For protons, this effect is much, much lower. The reason for that is that the average and maximum energy of the secondary electrons released by the protons is 3 orders of magnitude lower than for photons. So with experiments and Monte Carlo simulations, we showed back in 2019 that there is only a local dose increase of approximately 10% at 1 Tesla in the first few millimeters at this PMMA2 air interface. One slide on MRI-only based treatment planning. Different groups are looking into this. Different methods have already been explored to generate a synthetic CT directly from the MRI. So far, no experimental validation studies have been performed. And for proton therapy, we know that there are more strict accuracy requirements. It's more demanding than for MRI-only based photon therapy. Different groups are working on a conversion from MRI data into synthetic dual energy CT data, or even synthetic stopping power ratio, a conversion. Of course, the ultimate goal would be to be able to do to generate synthetic stopping power ratio maps directly on MRI data, and one of the postdocs in my group is working on this. One slide on real-time treatment adaptation. Of course, we would like to go for online adaptive workflows. So our initial workflows will be similar to the MR-LINAC, online daily adaptive correction strategies to compensate for interfractional changes. And then one step further in complexity is gating to compensate for intrafractional changes. For proton therapy, of course, this needs a dedicated workflow, especially if we want to use it for tracking, because that would require the full or the real-time full knowledge of the medium traversed. So here the challenge is to go from single slice 2D SINE imaging to 4D MRI conversion for 4D SPR. And I know that, for example, the group in Munich is working on this. Last but not least, how about this in vivo range verification? Wouldn't it be great if we could visualize the beam with MRI in real time during dose application? Well, we managed to do that in liquids with our 0.22 in-beam MR scanner. So here you can see MR images of a homogeneous water phantom that we irradiated with different beam energies. So I think you all would agree to me that you can see a signature of the stopping proton beam inside this water phantom. There is a clear beam energy, but also a current dependence. So the intensity of the signal that we get from the MR changes with the dose rate. And from these images, we can even determine the range of the beam with an approximate accuracy of 3 to 5 millimeters. But as I said before, we've only been able to observe these effects in fluids so far, not in solid materials, not in tissue, not in gels, not in mayonnaise. We tried a lot of materials. And the reason for that is that these effects that we are looking at here are induced by convection. And what we are actually looking at here is local flow effects that can be picked up with flow-sensitive MR sequences. So the conclusion is that this is not suitable for an in vivo application, although this signature or pattern in the MR image has a lot of similarities with the 2D dose distribution that was measured with the traditional film dosimetry. But at least we have an understanding of this contrast mechanism. And what we are now doing, of course, is to look into different MR techniques, different pulse sequences to make this technique more sensitive, such that it could maybe also be applied for in vivo applications in the future. I think for the sake of time, I will stop here. I have a few more slides on the potential clinical applications, but for the sake of time, I will stop here. If there are any questions, I'm happy to answer them.
For the excellent and very clear talk, really appreciate that. And of course, before we have the questions and discussion, which there will be many, I'm sure, could we please turn our cameras on so we can take our monthly Zoom photo? Angelica, if you could do that, please. So please, could you turn your cameras on?
Yes. Can you please stop sharing the screen so I can see all the camera that are on, please? Okay. Thank you very much. Just a second. Again, your best smile as usual. Okay, sorry, just a second. Okay, done.
Great.
Thank you very much.
Thanks a lot, Angelica. So, okay, so now we are open for questions, either by chat or by putting your hand up. So please feel free. It was so clear that nobody has any questions. Well,
I'll take that as a compliment. Thanks.
Well, I have a question, and that is, of course, you know, we're not able to show you clinical slides yet, but one of the challenges of the MRI-guided LINAC, which of course is wonderful, is the time it takes for the treatment, right? Yeah. And patient throughput is always a big issue. Yeah. So do you have a feeling of how the MRI-guided proton therapy might be in terms of timing?
Well, timing, of course, is, let's say, a relative issue in the sense that, of course, it will take more time on the machine to deliver the treatment because of the setup of the patient, the imaging that you do with the patient on the treatment table. And we know we also have an MR-LINAC here in Dresden, so we know that patient throughput will be reduced. But if we can show that the targeting precision, accuracy, and the targeting accuracy will increase, then this would open up the way for hypofractionation, which will mean less fractions in total. So I think we have to rethink this concept of using an MR-LINAC or an MR proton therapy machine for conventionally fractionated treatments, we should go for hypofractionation. And that will, of course, compensate a little bit for the extra time that is needed on the machine to do the imaging, to decide if a treatment plan adaptation is necessary, to do the QA online, and then irradiate.
So you can balance this. Peter has a question. Peter, please go ahead.
Thanks. Thank you, Aswin, for this really excellent talk on this exciting topic. One question was what already Manchit has asked, but I have another question related to this seeing the beam in real time. In the moment, it seems you are not so optimistic. What do you think? Will this be possible? First part of the question. Second part of the question, is there a better chance for heavier ions like carbons?
Oh, well, to start with your second question, I must say that I have not really thought about that simply because of the fact that we don't have the heavier ions here available in Dresden. So when we first started this beam visualization project and the results that I just showed, we had to apply a lot of dose at a very high dose rate in order to be able to visualize the beam. The first experiments were done in the kilogray range. And in the meantime, we have found a way to make this technique far more sensitive. So now we are at approximately a dose level of about 15 to 18 gray in order to be able to visualize the beam, which is in the range of a single fraction treatment for stereotactic treatments, for example. Yeah. But this technique that I showed here was still based on flow imaging. In the meantime, we have also done experiments that are based on oxygen depletion effects. This is also something that you could visualize with MR. And we are just putting together a new paper on this particular topic. It has already been shown that oxygen depletion can visualize a photon beam on an MR-LINAC. And we have repeated these experiments with protons recently, and we've also seen that it is possible to use oxygen depletion imaging to visualize a stopping proton beam in matter, not in water, but also in matter. How successful this translation into a clinical application will be is still, I would say, uncertain. It's a lot of speculation at this point, but we're working on it. And if someone has another idea how we could further improve this technique, I think this is, of course, let's say, the holy grail of radiation therapy, right? If we could visualize the beam during dose delivery, then we could close the feedback loop, because then we would really know what we are hitting. And this would allow us to also maybe steer the beam in real time to the position where it actually should be, which currently we do not really know.
Thank you, Aswin.
Mosley, he wants to know if it's possible using a field obtained by superconducting gantry for MRI imaging possible.
Ooh,
Good question.
This is a question that is beyond my field of expertise, I would say. A superconducting gantry for MRI. Absolutely. It's a challenging topic. Yeah.
Let's leave it at that. And then Gert, is the next question.
Yes, thanks again for this excellent talk again. I would like to come back to the topic of the imaging of the proton beam. I guess you're well aware that there are also efforts in ionoacoustic to detect the beam. Of course, that is then another technology, but maybe it is worth thinking about that and how the MR would then influence the diagnostics or the detector of the ionoacoustic, which might not be the case, but I don't know. Just thinking about.
There is a technique established in MR imaging that is called elastography. So this works in a way that you externally apply a pressure wave to tissue, and then the small tissue deformations can be picked up by what is called contrast phase imaging. This is also a technique, of course, that is of interest for us to look at these ionoacoustic effects. But so far, we have not had the time and the resources to look into this.
Thank you. Mimosa, please.
Hi, thanks to Oswin for this beautiful talk. I have just 2 ideas to share because I've got some ideas. First of all, if there is someone who is going to model this magnetic field influence on the beam, should take into account the self-induction of the beam itself. It is generating magnetic field, so it will interfere with all the others that was shown by Oswin recently. So it has to be in the model as well. And the second idea I've got is to use a bee wax, because I've seen in some of the British universities they are using in forensics to model a human body when they are researching the ballistics effect of a new weapon. So they're using it because its density is close to 1, close to water, and the melting point is about 60 to 70 degrees. So you can observe maybe the effects of the dose distribution probably in practice. Maybe you should try this.
So maybe that is similar to a kind of gel, I would say?
No, it's not gel, it's wax.
It's wax. Okay.
Just a solid state body, a wax. Women are using this wax for epilation. I mean, this is just commercial thing that you can buy in a market.
Yeah. But we
Yeah,
have
probably, but
we have to see if this wax produces an MR signal, right? Probably it will, because it will be based on, it will have some water molecules in it.
yeah, there is water probably. I hope so. Yeah.
And regarding your first comment, I know that the group in Munich, so Katja Parodi's group, has done excellent work on the theoretical modeling of the local magnetic field produced by a proton beam. The point is that the strength of that magnetic field is too little to be picked up by the MR scanners.
Okay,
so you need another technique to maybe with squids or something like that, but not with a conventional MR scanner.
Thanks.
Chat. So Eduardo wants to know, can this imaging be used for flash RT? Of course,
now
hot topic.
I will be a little bit provocative. So I showed you the what Professor Jan Lagendijk from Utrecht said back in 2014, that there will be no protons without MR. I would even go a little bit further and say there is no future for flash without MR. Because of course, if you apply a flash beam, you absolutely need to be sure where the tumor is at that point in time. So you need fast imaging for that. And their MRI could have an advantage.
The whole idea of flash is that it selectively attacks healthy tissue. So maybe the outline of the tumor is not so essential as you're thinking, but just being provocative, okay? Let's go to the next question. So Subjit says...
I can interrupt, but can you didn't answer my question, do you think, if you tried it, then you know, but if you haven't tried it, do you think that you could use the current setup, the protons and the imaging setup for flash experiments?
Yes. Not on our horizontal pencil beam scanning beamline because the dose rate is too low. But on our first beamline, so the static beamline, we already do flash experiments with zebrafish, for example, done by Dr. Elke Bayreuther. But so far, we have not done this in the presence of the magnetic field.
Thank you.
So the next question is, I presume this technique could be used for online adaptive therapy, right?
That's what we're aiming for.
Right.
Yeah.
Okay. And so the next one from Joseph. Are there any more reasons for using low to mid-range magnetic field strength except for having a high contrast to noise ratio for the thorax region?
That's an interesting question. Yes, there is, because I think that a higher field strength will only bring problems. Because the beam, the lateral, if the magnetic field is transversal, so perpendicular to the beam deflection will be larger. So you need to make more compensations for the presence of the magnetic field in your treatment planning. It will also have, it could also have a higher impact for certain for the responses of certain dosimeters, as was already shown by Hermann Fuchs. And yeah, why would you want to need a high magnetic field strength? We don't do diagnostic imaging. What we need, it's not about field strength. So for me, field strength is not the most important parameter. It is the gradient system. That is for me, that is the ultimate parameter of the MR machine. Why? Because radiation therapy is a geometrical problem. We just have to put the right amount of dose at the right spot. So for this, we need accurate imaging, geometrically accurate imaging. If you go to higher field strength, you'll have more magnetic susceptibility artifacts. So your images will not be geometrically reliable anymore.
Thank you. So I don't see any more questions. So I'm going to ask the last question, take the prerogative of chairing the session. And that is, we started off by saying that the precision is really important for moving targets, right? Tumors. So
Yep.
Since, we will not have so many of these machines at the beginning, if you had to have a selection of which tumors you would treat this way, what would be your first choice?
Well, let's say we could go for everything that moves in the thorax region. So esophagus would be a candidate, but also, for example, renal and adrenal tumors, and maybe even pancreas.
That would be really important because, as we know, that's a really difficult one.
Yeah.
Right?
Yeah.
Okay, so anyways, I think thank you once again for an excellent talk.
Thanks.
Telling us really the reality of the situation and clear explanations. And thank you to all of our listeners and participants for joining in. So 2 things, this seminar will appear on YouTube, so please feel free. And second thing is, we are always looking for really interesting talks. So if anybody would like to contribute, please contact me. And otherwise, thank you so much for the excellent talk. And thank you for all the people who are staying behind. Looking
Thank you.
forward to seeing everybody in the next month. Okay, thank you. Bye-bye.
Thanks a lot, Aswin.
Bye-bye.
Have a nice evening. Bye-bye.
Bye-bye.